Hello, Hubblers, and welcome to this week's Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute, and we've done it again. We've got another great hangout planned for you this week. Astronomers, using Hubble and a variety of other telescopes, have looked at some 20,000 galaxies, a little bit more than that, in an attempt to try and understand a little bit more about our own Milky Way galaxy. These are all galaxies that they've looked at individually or in different ways to try to build a story of what our galaxy was like. And we're going to learn about what that story is in just a little bit. I'll introduce him in just a second. But before I get started, let me introduce my co-conspirator, Scott Lewis. He's the internet driver for us, and he monitors all the comments and questions. Welcome, Scott.
How's it going, Tony?
Really good. Carol's not here today for reasons I'm not sure. I think she's on assignment, so hopefully we'll see her next week. But
she's at Hubble. She's up in orbit right now, putting a little thumbnail at the bottom for every picture of her just winking at us. So from now on, every image from Hubble will have Carol winking.
There you go. Oh, there's a thought. Okay, so
I'll do it. Photoshop is my friend.
All right. Well, so before we get to introducing our guests, let me get to a couple of announcements. Hubble Mania is over, and thank you all for voting and everybody who's participated. Turns out the Pillars of Creation was the winner, which I suppose is not a surprise. It's a very iconic image, and for those. Throughout the Hubble Mania campaign, our graphic artists have put together posters that you can print out and download to sort of celebrate Hubble Mania, but it was a big success. Lots of you participated, and we want to thank you for that. The link is down in the description box, I think. I hope I put that in there. If not, it's hubble25th.org/go/Hubble Mania. And then also, the Ode to Hubble video contest finalists have been announced, and that link I did put in the description box. There are two categories, those of you who are under 25 and those of you who are over 25, and they've selected the finalists from each category, and they will announce.
I watched a few of them. They're awesome.
Are they?
Really, really good. Yeah.
Yeah. Cool. I need to get over there and watch. I watched a few of them when the voting was going on, but I didn't see the finalists yet, so I'll have to check that out. Anyway, they'll be announcing the winner April 24th, and the winners will get, there'll be two, one in each category, and they will get a piece of the solar array that was actually on Hubble when it was taken down on one of the servicing missions. So that'll be a great prize, I think. So watch out for that. And let's see. Oh, the third episode of the Hubble 25 videos produced by Mary Estacion has been posted on YouTube. That link is also in the description box. She will be releasing one video every month for the entire year, all in celebration of Hubble's 25th anniversary. So we hope you'll check that out as well. Okay, today's hangout is about the Milky Way, or at least galaxies like the Milky Way. One of the more challenging things about astronomy and studying the universe is that things take a really long time to happen. Stars take anywhere from 100 million to 1 billion years to live their lives, and galaxies, the same kind of time scales. In fact, we're going to talk about the different kinds of galaxies out there and how long they live, but some of the oldest, like the elliptical galaxies, are almost as old as the universe. So how do you find out? Because by comparison, we're only alive in a blink of an eye in that time. It's 80, 90 years if you're lucky, and or 110 in my case. That's what I just turned 110 today, so I'm going to be.
Congratulations!
I don't look a day over
109. 109. Yeah.
I know.
I know that.
So thank you.
Before we get into it, though, let's remind our audience too and how they can get in touch with us. So if you're looking to interact with us, we are totally interested in answering your questions and seeing your comments. So the ways that you can do that is if you're watching us right now on either YouTube or Google+, you will see on the bottom left some yellow text saying that we are answering questions live. It'll allow you to use the Q&A app to ask us questions. I've already got it up there, and I'm seeing one comment that's already in here. So that's a great way for us to interact, and actually timestamps it when we're answering your questions. You can leave us comments like you normally do over on YouTube and also on Google+, and then also over on Twitter. We are using the hashtag Hubble Hangout, one word, and we will be. I'll be monitoring those, and we'll be live tweeting the Hangout as we're going out from our account at Hubble Telescope. So that is the. We prefer the Q&A app because it allows us to see live when you guys are doing it, but I love the Twitter conversations that have been happening lately. So please tweet at us, and I might just retweet you if it's awesome.
Yeah, that'd be great. Thanks, Scott. And if you don't follow us on Twitter at Hubble Telescope, please do. Also subscribe to Hubble Site channel on YouTube, and you'll get all of the information on that. Also, Cosmic Carol, I saw your tweet about must not get distracted by deep astronomy bookshelves. It's okay.
It's fake. It's just a poster.
It is not fake. Those are real, and I've read every single one of them too. Okay, so today's hangout, folks. In order to understand something that happens over hundreds of millions or billions of years, astronomers have, while we won't be able to just stare at it and see it in our lifetimes, astronomers have some tools that they can use to kind of get a picture of what the lifespans, what happens in various parts of the life cycle of different objects like stars and galaxies. And what our team of astronomers have done today is they have looked at some 24,000 galaxies, and of those, managed to pick out about 2,000 or so that were like the Milky Way and in various stages of their life to try and attempt to build a picture of what our galaxy was like. And they found some really cool things. So let's talk about it right now. With me also is Casey, Dr. Casey Popovich. He's from Texas A&M University, an astronomer slash astrophysicist, I assume.
Yes, of course. So, hi, Tony. How are you?
Yeah, one of these days I keep meaning to ask to talk about the difference between the two. Also with me is Harry Ferguson. He's an astronomer at the Institute, and he's a very I love working with him. He's been in our hangouts. One of the first people that was ever in one of our hangouts. So welcome, Harry. Also is Ryan Quadri. He's also from Texas A&M, and they're here to discuss what they've done to the universe. So who wants to start? How about you?
What have you done to the universe, guys?
Yeah.
Just so you know, some of my friends here at JPL are Aggies, so I'm sure they will be very excited to know that you guys are on today.
Yeah, I'm sure. So
why don't you give us a quick overview of what the press release was about today?
Yeah, sure. So this is it was a combination of many different surveys that we have going on, but it focuses really on a big one from Hubble, which is the Candle survey using the Hubble's new infrared imager. Hubble, surveyed all these different fields, getting very deep images. We then combined it with a whole bunch of other data to find galaxies, as far back in time as we can, and we began to find ways to link them together. We get these snapshots in time of what different galaxies looked like, and we started to piece those together to figure out which ones would be most like the progenitors of ones that we see maybe today and nearby, like the Milky Way, for example.
Great. Okay, so you mentioned candles. I'd like Harry, give us a comment a little bit about what candles is. It's one of the surveys that Hubble has been involved in, but give us a little more specifics. You're muted.
Push that by accident. Thank you. So people may be familiar with the deep fields where Hubble has pointed to a tiny, tiny patch of the sky and just taken exposure after exposure for a week or two and added them all together. And those are great, and I love those, and I've worked on those, but they're such a tiny piece of the universe that they're not as representative as we would like. And galaxies like the Milky Way are actually pretty rare. And so we need to survey a wider swath of the sky. And we can't invest that much exposure time, so it's shallower exposures, but over much larger areas, 100 times the area more or less of the deep fields. And so ours is sort of it's a statistical survey, taking a bunch of infrared images and then adding them to a database of the optical images that we took of these fields over the years before. With the Hubble ACS camera, and then a lot of information from other telescopes, including the Spitzer Observatory, the Herschel Observatory, the Chandra X-ray Observatory, ground-based telescopes. These are the sort of watering holes in the sky where everybody is going to study galaxy evolution.
I like that. I like that analogy.
Yeah.
That's really cool.
So we've been putting the database together and then starting to mine it, and this was one of the I think one of the things that we'd hoped to do all along was see if we could put together a storybook of what the Milky Way was doing, and Casey can describe in more detail sort of this approach, which right now looks like the most promising way to make the connection across cosmic time.
Awesome. Well, I will get to those specifics in just a minute of some of the things you found in this particular study. But let's now that we have a sort of a general picture of what we're doing and how we got there, Ryan, let's take a quick step back and talk about just galaxies in general. Let's get some basics in on the kinds of galaxies. Now, I've always heard it said, and I learned this from Sean Carroll at Caltech. So there's about 100 billion galaxies in the universe, more or less. I mean, it's a good round number to use.
Sure.
And Harry just alluded to the fact that Milky Way type galaxies, by comparison to all the other galaxies in the universe, are relatively rare. What are some of the different kinds of galaxies that are out there, and when did the galaxies first start forming? Was it a right away, or did it take a long time?
Well, so in the nearby universe, that's the present-day universe, there's a wide variety of different types of galaxies. Do we have that the image of the Hubble tuning fork?
Yeah, Scott will put it up for us.
Okay. So Edwin Hubble, famous astronomer, we've all heard the name at least.
Who?
Edwin Hubble. Who
that guy is.
I hope they don't name any spacecraft or telescopes after him, because that would just be cheesy.
Yeah, I think he's a telescope dealer. Anyway.
So he developed this classification scheme. We call it the Hubble tuning fork, and you can look at the graphic and understand why.
Okay, how do you read this? Do you go from left to right or right to left, or?
You start anywhere you would like. I'll start on the right. That's the spiral galaxies.
Okay.
So these tend to be lower mass galaxies, and these galaxies, the stars arranged in a disk, and you often see these the spiral structure. And as you move to the left, the galaxies, the disk-like structure becomes less dominant, and the galaxies have a central bulge that becomes more and more dominant. And as you get all the way to the left, the disk is pretty much gone, and all you're left with is this giant bulge. And so there's these galaxies, every galaxy is unique. Galaxies are complex systems. Every galaxy is a snowflake. But we can sort of group them into these coarse groupings based on their structure, based on their mass. And the Milky Way would be, it's a spiral galaxy, but it has a quite dominant bulge. So it's sort of maybe an SA or an SB galaxy on this classification scheme here.
Okay, so the S stands for spiral, the SB at the bottom, that's barred spiral, is that what that is? Or
that's right, yes.
Okay, it's got that bar characteristic, or sort of like a little line through it or something like that. So, and the A, B, and C are just letters, right?
They're just letters corresponding to how dominant the bulge is.
Now, does this diagram say anything about the galaxy's age? Are the SC galaxies, for example, much younger than SAs, or are E0s the oldest? Or?
Yeah, that's an interesting question. Way back when this classification scheme was first developed, the thought was that galaxies moved from left to right. They started out as the ellipticals, and then they sort of spun up or something and developed the disk-like structure. But now we think that it goes more, if anything, in the other direction. Galaxies start out small. They're actively forming stars. The stars are forming in a disk-like structure. And then something happens as these galaxies evolve. They start to form bulges. The disk becomes less dominant, and you end up with an elliptical galaxy.
Cool. So the masses and the little bit about the ages can be thought of in this scheme here. So so what about does it say anything about the amount of dark matter that's in these galaxies too? Because I know that, well, I guess it would, right? If they're more massive, they would have more dark matter, correct?
Yeah, that's exactly correct. So galaxies are thought to be surrounded by a lot of dark matter. We call them halos of dark matter. In fact, the galaxy itself is small. Small means thousands of light years across. But they're embedded in these much larger halos of dark matter. And it's thought that the dark matter somehow regulates and drives the galaxy evolution. And perhaps it's even related, perhaps the amount of dark matter that there is somehow related to whether a galaxy is a spiral galaxy or an elliptical galaxy. The thought is that elliptical galaxies have much more dark matter than the spiral galaxies.
Okay, Casey, let me ask you real quick. Based on, let's go back to what I asked at the second part of my question was, were these galaxies created our galaxies created pretty soon after the universe was formed, or did we have to wait a really long time to see the first galaxies?
Well, I mean, we had to wait a really long time to see them because it's only been now that we can actually.
Oh, well, I mean,
I like this guy.
Yeah.
Well, it depends, of course. We're talking about astronomical timescales, but as far as we can tell, galaxies formed pretty quickly after the Big Bang. Certainly within the first few 100 million years, as far back as we can see with Hubble, we are able to detect some of these, first galaxies forming their first stars. And of course, this is really going to be the realm for James Webb Space Telescope, something else you guys may have heard about. Yeah.
Yeah, I think we.
Yeah, they start forming right away.
I think we've heard of it.
Yeah, we've heard
sure you have.
Yeah. Okay. So, talk a little bit about this idea of looking back in time. Everybody, we often say that in astronomy that the most distant galaxies were among the first to be seen because when we look back in time with telescopes. Explain how that is. What's the idea?
Yeah, that's great. So basically as we look out into the universe, we see farther and farther away. And because they're far away, I mean, these are billions of light years away in some cases, these galaxies that we're seeing. The speed of light is fast but finite, and so as we see a galaxy that's more distant, we see it as it looked when the light left it. So if it's 10 billion light years away, it took light 10 billion light years to get here, so we're seeing a snapshot of that galaxy as it looked 10 billion years ago. And if the universe is, almost 14 billion years old, then we're seeing a snapshot when that galaxy was when the universe was only 4 billion years old, as opposed to when it's 14 today.
Yeah, Scott has an example of what you're talking about up here. Describe this diagram or this image that we're looking at here.
Yeah, sure. So this is actually a nice piece of artwork that I think the people there at the Space Telescope Institute put together based on the work we did, which is really linking together what we think of as the typical galaxies that are the progenitors to something like the Milky Way. So we track them back in time. We find the ones that we think are most characteristic of the progenitor of a Milky Way-sized galaxy. They're scaled so that it's a physical size. So 1 inch on each one of these panels corresponds to the same number of light years. Well, it's thousands of light years. But you can really watch both the physical size grow up, so just how big the galaxy looks, as well as seeing how its colors change with time. And as we see them as it looked 11.3 billion years ago, the first one right there on the right, it's very small, compact, and as just time goes by, it's right to left. Right, I don't know why we do everything right to left here today, but we're reading everything right to left here. Time is going by, so you're seeing the oldest, well, really when the galaxy was youngest. So we're seeing the most distant snapshot is all the way on the right, 11 billion years ago. And then time is just going by as you move from left to right. Slowly, the galaxy gets bigger. The color seems to go from white to yellow and then kind of get redder as you move along. And that's actually telling us a lot about the nature of how the galaxies form their stars, throughout its history.
So at a glance here, we're sort of seeing that the older galaxies are smaller. They're different colors, and as they get closer to present day and closer to us, they get larger and their colors just sort of shift in a variety of ways. So each one of these panels is kind of characteristic of its time period then for spiral galaxies?
For a spiral galaxy with the mass, what we think is the Milky Way. So that's
okay.
Exactly right. Yeah.
So Harry, you went through 20,000 some odd galaxies here. Now, you didn't do this manually, right? How do you identify these galaxies? Can you give us some idea how that's done?
Oh, I didn't do it at all. Casey went. Yeah.
You had him look at 20,000 of them.
Yeah.
You supervised.
Yeah.
Very good.
The trick here is you're trying to figure out what galaxy might have evolved into the Milky Way, and so if you make an assumption that you can count down from the most massive galaxies to the least massive, and if you take a little patch of the space that's always the same volume, and then you say go down to the 100th galaxy in mass, and you're just sorting them by our estimate of stellar mass. And then you can say, well, it's probably likely that they're not changing their ranking much over time. So if I track the 100th most massive over time, that might be a pretty good guess as to what the progenitor of today's 100th most massive galaxy is. So that's the trick Casey used. And then he took a sort of a range of mass around that ranking, but it's basically a rank ordering and trying to figure out where the Milky Way is in that ranking today, and then tracking that ranking back in time. Then you probably got a pretty good picture book. And there's a lot of debate about whether galaxies swap ranks, and they probably do it a little bit at some level, but maybe not enough to change the picture. Yeah.
I'm not getting what you mean by rank. You mean there's some what? Yeah, I'm still not.
Yeah. So go to the slice of the local universe and go out to some distance, and that gives you a volume. And we know that volume pretty well from surveys with telescopes nearby. And now you can say, from various studies of galaxies, you can estimate how many stars they have in them. And you just sort them from the galaxy that has the most stars down. And the Milky Way will be somewhere in that list. And that's its ranking. And it's not going to sit near the top, but it's going to be maybe the 1,000th most massive galaxies in that volume or something. So you're going to track it that way.
I see. And so it won't necessarily always be in that same category or same rank in the list. It might change. And that's so. Casey, what's the punchline? What did you guys? So you guys looked at all these galaxies. You ranked them, and you figured out from most massive to least massive, and you tried to build a picture of the history of our galaxy. And what did you conclude?
Yeah, exactly what we did. And Harry described it actually really well. It's very much the technique. So the snapshots that Scott showed a little while ago actually encapsulate a lot of the findings from the study. So we found the galaxies. We actually now have what looks like a mass history of how our Milky Way galaxy grew. It's the number of stars it has in it over these 11 billion years. We can do other things with them. So one of the great things about working in these candles fields that Harry was talking about at the beginning is just a wealth of multi-wavelength data. They span all the way from Hubble all the way through Spitzer and Herschel, where you get an idea of the far infrared emission coming off these things. And that's great, and we actually looked at that because the far infrared then tells us a good idea of how much light is coming out from newly formed stars at each one of these snapshots in the past. And so then, not only do we get an image of what the galaxies look like, now we know how much mass they have in them, but we get a measurement of how fast they're forming their stars at each one of these points. And that whole picture seems to hang together. Because when you look at how fast they're forming their stars over 11 billion years, and you kind of add up all the stars, you get something like the mass of the Milky Way today. And that didn't have to happen. That just seemed to be the way the data guide us here. And so we actually put together a nice picture of not only how fast, what the Milky Way looked like in the past, but actually how fast it was assembling itself over all the time.
Okay, so one of the things you found was that the rate of star formation was not always the same, right? There were. Go ahead. I want you to. That's the punchline. I want you to talk about.
That's the punchline. Yeah, that's exactly right. That's exactly right. Today, we think the star formation rate, so how fast is the Milky Way forming new stars, is pretty low. It's about 1 star per year, on average.
That's the current rate today.
That's the current rate today. Yeah. And other galaxies like the Milky Way have rates about the same like that. So today, they're forming stars about 1 new star each year. In the past, right around, let's see if Scott, if you put that image back up, I can actually show people. In the past, right where it says, between 9.5 and 10.5 billion years ago, the rate of star formation was about 30 times higher. So instead of 1 new star per year, it was forming 30 new stars per year.
Wow.
But one way I've talked about this before is, sort of like the way humans grow. At the beginning, you grow really fast and quickly. Babies double in size. It seems like every week. But then all through adolescence, you're growing pretty fast. But then as you get older, your growth tends to slow down. Well, at least we hope it slows down for many of us. But
yeah, I just want to point out, Casey, that your audio is getting a little weird for us. I'm starting to hear some clicks or something like that. So I don't know. Maybe after I move to someone else, maybe you can mute and unmute and see if that fixes it and goes. But
unless he's half dolphin, and that would explain the clicks.
Oh yeah, that's right.
Half dolphin, Casey.
He's tending to the dolphins in the audience. Of course.
The dolphin.
Yes.
I see. Okay.
Yes. Yeah. Okay.
Right.
So Ryan, can you comment on this a little bit? I mean, so there was a period in by looking at these galaxies at the various stages of their life cycle, we found that there was a period where they were happening about 30 times faster than today. How long ago was that, roughly?
So it was a long time ago. So the universe is about 14 billion years old right now.
I could have said that.
And sort of, so the heyday of star formation of the Milky Way ended maybe something like 8 billion years ago.
How old's the Milky Way? Let's go. Let's just start there too. How old?
How old is the Milky Way? That's a very interesting question, and it's sort of.
Is there an interesting
we can't really say. When did the first progenitors of Milky Way-like objects form? When did they separate from the cosmic expansion, collapse, and start to form an actual galaxy? We can't actually address that with our current data. With the James Webb Space Telescope, the successor to the Hubble, we should actually be able to see the first stars that form. Using the current data, the furthest back we can push is maybe 10, 12 billion years ago. And by then, the Milky Way already had a billion stars, or billions of stars. So
wow.
we're not actually capturing the birth and the infancy of the Milky Way. We're sort of, we come in at childhood, and we can only probe since then.
So the Milky Way is just about as old as the universe, then, is what you're saying.
Close to it. Yeah, close to it. So, yeah, we're pushing back maybe 12 million years ago. The universe, Big Bang was about 14 billion years ago. So we can get almost all the way back, but not quite there.
So, Harry, can you give us an idea of the conditions that might need to exist for a spiral to form? I mean, not all galaxies start out as spirals. I remember seeing in some of our other hangouts, there were pictures of the first galaxies. We had Massimo Stiavelli on here, and we were looking, and they just looked like wadded up clumps. They don't look like much of anything. What conditions need to happen for it to be a spiral? Do you know, or does anyone know?
Well, we have some ideas, and I would say that the picture you should have.
Uh-oh.
Uh-oh.
That's what he gets for trying to tell me what to do.
There you go. You froze up.
You're back.
Froze up.
You're back.
Okay, so the Milky Way.
Nope.
Uh-oh. I hope he's not on wireless. I should have meant. No, we're not hearing you. We're not hearing you, Harry.
In and out. Okay.
Oh, yep.
I'm gonna plug in.
Yeah, try to get to a wired connection if you can. And Casey, can you follow up with that? Can you talk a little bit about where he was going? Like early conditions. What determines the kind of galaxy we end up with?
Yeah, that's a really good question. I would say a lot of our recent work, this is really, even using the Hubble data just from a range of projects, suggests that galaxies actually evolve pretty much the same way. And how much mass they have dictates a lot about how their visual appearance is going to look. We certainly know that when you look back in time, so we're seeing these, the early stages of the universe, the gas fractions in galaxies was much higher than it is today. So
and that's important, right? Because that's going to determine what stars get formed.
Yeah, that's exactly right. I mean, stars don't form out of thin. Well, yes, they do form out of thin air, quite literally. They don't just form out of vacuum; they form out of gas. And so, gas falls into these galaxies, and it cools and collects into these disks. And then it begins to form stars. And over time, those disks build up. And once the disks get big enough, then you would begin to see some of these spiral patterns and things showing up in the Hubble data. Before that, they might be there. We just can't resolve them.
So how long was this peak in our galaxy's history of this rapid star growth or star birth?
Good question. It was possibly as long as 1 billion years.
So for about 1 billion years, something happened in the Milky Way that caused all these stars to be formed 30 times faster than ordinarily would. What was it? Do you know?
Yeah, that's a good question. I think it's a combination of several things. No doubt the amount of gas the Milky Way had was a lot higher, and that just drives it. So if you have more gas, the gas is there, more stars are able to form. So that's the first part. So today, the Milky Way has consumed most of its gas. So that's one reason we get this big slowdown. The second effect is that the universe has just gotten a lot bigger over the 10 billion year time span. The universe is expanding. In fact, it's accelerating, if anything else. And so a galaxy's ability to get new gas from the intergalactic medium is just diminished because everything's farther away, and it's hard. The amount of gas you're getting over time is just slowing down.
So that's a good point, actually. So as the universe was smaller, it was easier for these galaxies to accrete the interstellar gas or intergalactic gas that maybe had left over from the creation of that wasn't already a part of a galaxy.
Right. That's exactly right.
But what confuses me about this is it would seem to me like when the Milky Way was first accreting and gathering its stars, it pretty much defined its mass early on, right? I mean, why wouldn't you have had rapid star formation at the beginning instead of some interval after it was born?
That's a good question. It's because there are limitations to how fast you can form your stars. So we actually think that the rate you can form stars is tied very much to how fast you're accreting new gas. Those two kind of couple together. So when you're small and you're smaller mass, you have less gravity and you accrete less gas. But as you build up your mass, you start to accrete more and more gas just because you get more and more massive. So as a result of star formation, we kind of follow that growth.
Okay, all right. Well, so Ryan, what about dark matter? Does dark matter have any role in this, or has it pretty much gotten all of its dark matter when it was first formed, or is it also accreting as it gets older?
Yeah. So as I said earlier, galaxies are embedded in these halos of dark matter, and the halos of dark matter weigh much more than the actual stellar and gas material inside the galaxy. So it's the gravity from the dark matter that really is responsible for sucking in new material, for sucking in more gas, for sucking in fuel for more star formation. And so dark matter has to be implicated in some very fundamental way in this whole picture. We don't have a perfect understanding of that, though.
Oh, okay. All right. Well, there's a question here on the Q&A app from Dan Buda. Let me ask it real quick here. Does the black holes in the middle of almost all galaxies are formed after the dead of the first generation of stars? In other words, how long after the galaxies are formed and have generations of stars do we start to see the supermassive black holes at the center? Are they from the beginning, or do they form later?
That is a real topic of current research.
Oh, okay.
It's a chicken and egg problem. We think we see that they're coupled together because the more massive black holes are in the central parts of galaxies and their mass more or less scales with the mass of the stars around them. So they're probably both growing up from smaller seeds over time at roughly the same rate. And that means when you have a baby Milky Way with not that many stars, it probably has a baby black hole in it, but that black hole, is still pretty massive, more massive than a stellar black hole.
And always hungry.
And always hungry,
always
exactly.
Hungry.
Good question, Dan. Thank you. So you sound much better now. Hank. Harry. That's a word.
Francesca, we'll call you what we want.
Don't make fun of me. I had a senior moment there.
Well, you are 110, so you're doing really good.
Yeah, I am. So far, I'm doing really good with this. So, can we follow up a little bit? So before we were about to go live, we talked a little bit about the mass of and Casey, you can comment on this as well. There was some argument about what the mass of the Andromeda Galaxy. The Andromeda Galaxy is what a lot of people call it our sister galaxy, and it's also one of the closest to us. You were saying something about there being some controversy about how massive it is. It's amazing to me that we still don't know as much as we do.
Right, I would agree. It's actually pretty amazing to me as well that we still have some debate over how massive galaxies can be. So so our own Milky Way galaxy, maybe it's no surprise, it's actually hard to get a complete picture of it because we're embedded inside it, and so we can't see the whole thing at once. We just see a little snapshot where we exist. Our sun, rotates around the galaxy embedded in the disk. We can see the Andromeda Galaxy better. It's still a controversy, I would say, about, or maybe it's a debate about what exactly how many stars are in the Andromeda Galaxy. I say it's a debate, but it's probably pinned down to about a factor of 2 or so. And it ranges anywhere from, what we think, how many stars are in the Milky Way Galaxy. Which is, anybody else want to get a gamut at that one? That's a hard question to answer, too.
Billions and billions.
Billions and billions, yeah. A few hundred billion.
Let's say again and just say it's billions upon billions.
So, humans have a hard time with numbers greater than about 5, so I know it's more than 5 stars.
Yes.
and it's somewhere in the billions, but at that point it's just a very large number. But we think Andromeda, if anything, it's at least as big as the Milky Way, probably twice as big as the Milky Way, and we have some evidence of that because the center of mass of the Milky Way Andromeda system seems to be closer to Andromeda than to us. Although that's the evidence people are using.
Okay, and a lot of people seem pretty confident about our ability to measure dark matter too, which I know plays a big role in.
Tony got muted somehow, and it wasn't by me. Let's see here. So, yeah, Tony, I don't know what you did or if Elena did it, but you are completely silent, and I believe your camera is hidden as well. So, as that's going along, I'm going to check out some questions here on Twitter. I'm not sure, Elena. I'm getting some questions here. So let's pull these up here. I can't select them, but perhaps they can be put up there. This is from Juan Berda. It says, in the image sequence of the galaxies, you mentioned that they are all to scale. Does the fact that the universe was, quote, smaller back then affect the way you determine the scales of the old objects? It looks like Tony's back.
Yeah, I have no idea what happened there, folks. I mean, I was talking and it said, it just flat out was, you're no longer part of the broadcast. And it just like, that's all it was. It's like, oh, okay. Anyway, go ahead. Yeah, that's a good question. Go ahead. And did you want to take that one, Casey?
Yeah, sure. I can take a first stab at it, and Ryan or Harry can jump in and mess it up. But we do take into account the fact that the universe is much smaller back then. So I mean, when we look at it, all we see is the angular size of the galaxy. So how big does it look in these Hubble Space Telescope images? And then, based on how far away it is, we can do the geometry in an expanding universe to take out that expansion. So when I say they're to scale, I mean they're actually the same, what we would call a proper distance. So it's the same physical scale in each one of these redshift planes. So in other words, 1,000 light years would be the same number of inches in each one of those panels. After we divide out the expansion. That's a really good question.
Yeah, thanks.
That was a really good question. I was wondering that myself.
Yeah, I want to have a hangout at some point about the shape, the geometry of the universe. I heard it's a very difficult concept, but it turns out that the shape of the universe, which is sort of an unbounded, has an unbounded sphere, I guess, or something, is different than the geometry of the universe. It's a different concept, and separating those two out is a very important thing that astronomers have done, using trying to figure out they've used the microwave background geometries and a variety of other methods for determining that basically the geometry of our universe is flat, and dark energy plays a big role in that as well. But that's a little off topic here, but it is a you mentioned it, and I just wanted to point out that is a very difficult thing to visualize, is the actual shape and geometry of our universe. Okay, so what if anything does your work tell us about? You've done a pretty good job constructing the past in terms of star formation. We went through a period of about 10 billion years ago. We went through 30 times the rate of star formation that we have now. Now we have stars today being born at about 1 per year. Surely you've seen images of galaxies in your survey that are older than the Milky Way. Can you infer something about our future from this using these techniques?
Stop calling them Shirley.
Harry, Ryan, do you guys want to take this? I mean, I can take a stab at it too.
Let's do Harry. He's been quiet for a while.
Okay.
Oh, I was hoping you'd do Ryan. So it's a subtle question, because the age of a galaxy is such a sort of ill-defined thing. So if I want to choose to say the age of the galaxy is the age of the bulk of the stars in it, which is it's a convenient definition, then there are certainly galaxies around us that have older stars on average than the Milky Way, and they by and large have a bigger central bulge. They're redder, and they tend to lose their well-defined spiral structure, so they have less gas, so you can't see the spiral structure, and they're not forming the young stars, so even if they still have a disk, it looks sort of fairly smooth and boring. And that's probably where our galaxy is headed, although it may or may not form a big bulge, because that bulge, we think, comes from merging, or at least that merging is one of the paths to get a bulge. In the late universe, where the galaxies are so far apart, that doesn't happen much. On the other hand, eventually we'll merge with M31, the Andromeda galaxy, and then we may very well become an elliptical.
Yeah, that is, if it's twice as massive, then it would definitely add quite a bit to our bulge. Much like I'm thinking now about drinking beer and getting a beer belly, but
Yeah, yeah, same sort of thing.
that's so you brought this up, and I want to talk about this a little bit. Galaxy mergers, interactions, collisions between galaxies. What does that do to the rate of star formation, if anything? And I'll let anybody who wants to take that one. Ryan, maybe you could do that one.
Sure. So this is one of the This is an interesting point in galaxy evolution, and our study actually gives us some good data for this. So galaxies, they form stars, they continue growing, they can also merge with each other, and if two galaxies merge, if each one has plenty of gas, plenty of fuel for star formation, all these clouds of gas collide with each other, and that triggers more star formation. So a merger will not, if you merge with a galaxy that has the same amount of mass as you, your mass will double, plus you'll undergo a new burst of star formation. Now, there's a long-standing question, how important are these mergers for the overall evolution of galaxies? Are they rare events, or are they actually a dominant factor? And one of the things we found in the study is that most progenitors of the Milky Way have this disk-like structure. Okay, that means there can't be too many mergers going on, because if you take two disk-like galaxies and you collide them, the disk-like structure is going to get all messed up, and everything's going to go to hell. You'll have an elliptical galaxy. But the fact that most of the galaxies in our sample have a very prominent disk-like structure says that mergers can't be happening all that often.
So its spiralicity, I guess, if you could use that word, is sort of an indicator of how many galactic collisions it has experienced so far. Not too many in order to keep that shape. That's an interesting idea. If you leave a spiral galaxy alone, let's say that by some strange, since we don't know how common collisions are, if you leave a spiral galaxy alone, let's say it doesn't have any collisions ever, is it going to always stay a spiral, or will it eventually become one of the other things in that tuning fork, which was the end of the road, which looks like elliptical galaxies? Or do you need these galaxy collisions to make that blob?
Yeah, that's a difficult question, and I don't know that we have a completely good answer. It does seem that what we call secular processes are capable of building up a bulge. You can start with a spiral galaxy, and somehow it transfers material inward and forms a bulge. So you can start to transfer, you can build up a bulge and reduce your disk by purely secular processes without mergers. But can you form a full bona fide elliptical galaxy? I'm not really sure, but probably not.
Well, I mean, it would sort of stand to reason, though, that because these ellipticals are so massive, I mean, they're among the largest galaxies in the universe, that they would need to accrete other galaxies or gobble up something along the way to get that way. And it would also make sense to me. It's just just the way my mind works, I guess, is it would constantly colliding and bombarding the galaxy with other galaxies would eventually just make a big mess. And
and as we're talking about this, I do want to share one of the videos that we have out on Hubble Site channel that I believe Frank Summers did with some simulations, but also some observations as well of galaxy collisions. Let me see if I can get this queued up here. Here we go. So this is here some simulation data.
Yeah, that's from Frank. Yeah.
Yeah.
Yeah. So yeah, this is one of my favorite. Yeah, this sort of shows the interacting galaxies, but Ryan was saying we don't really know how common that is, right? Is that so? Do you have anything to add to that, Harry? Is there any indication of how common these galaxy collisions are?
We have it's an interesting question. I mean, we have a pretty good estimate from our theory of how often the dark matter halos collide and merge. The problem is we don't really know how long it takes for the galaxies to look like separate galaxies or become sort of merged into one. And so when we go out and try to find things that look like this picture, this simulation in our observations, which we are very actively trying to do, and we count them up, we can get an estimate from the merger rate. But then we need supercomputer simulations like these sort of visualizations to tell us how long the process lasts. And so it's this combination of theory and observations that's we're making progress, but I would say we still have uncertainties of factors of a few in what the merger rate of the sort of visible parts of galaxies is over time.
Great. Okay. Well, that's really thanks, Scott. It's good to put that up. I'm glad you did that. It helps us visualize the collisions a little bit better. So, Casey, your paper came out today, you found this information about the history of star formation in our galaxy. What's next? What are you going to do? Some follow up, or is this? Are you done?
Oh yeah, that's a great question. I mean, so I think there is a lot more to do with this. So one of the things I think we've done really nicely now is seeing how the average evolution of a Milky Way-like galaxy looks. And Harry kind of alluded to this before. We know that actually a good question is how many galaxies actually follow that average evolution, or is there a huge variation in there? I suspect there's a huge variation, that galaxies can have many different pathways to becoming something like a Milky Way galaxy. I think we know that because the Milky Way itself may be a big outlier for galaxies like the Milky Way. So what I mean is, if you go if you go and look at
so even among spirals, it's a weirdo.
Even among spirals, if you go to the Sloan Digital Sky Survey and just say, give me all the galaxies nearby, very low redshift, very very local galaxies that have a similar mass to the Milky Way, they may be more bulge-like. Have larger bulges, like what Harry and Ryan were talking about, and less prominent spiral arms than the Milky Way itself. So our Milky Way may actually be a latent comer in the sense that it's still forming stars faster than some of these other Milky Way-sized galaxies.
Our galaxy's fitter, right? Less bulgy.
Yeah, that's right. Our galaxy is more extra-sized. That's right. That's right.
Okay. All right. Well. Okay, here's a question I would like to ask. I'm glad this comes up because every once in a while I like to address this in our Hangouts about what kinds of things are necessary to become an astronomer. And since I have 3 of them on here, this is from Shamini Laganathan, I think. Forgive me if I messed it up, but he's asking. I really want to work in the astronomical field. He wants to become an astronomer. But what higher studies should I take to achieve it? His ambition is to become an astrophysicist. Or it could be her. I'm not sure.
I can give some.
Yeah, give some advice to people who are looking to get into astronomy.
It's great. I would say if it's your passion, you should definitely follow it. I mean, that's probably true for everybody.
But almost everybody's scared of the math. I mean, everybody's like, every time I've talked to somebody, they're like, oh, I can't do math. I can't do math.
Well, there is a lot of mathematics, so there's a lot of that. I would say any more of it has gone more and more toward computer science. Thanks to people like Harry who are designing these huge surveys with Hubble. I mean, Harry, how many galaxies are in just the Candles fields? Tens of thousands.
It's about 250,000.
250,000. And so, having the strong background in computer science, statistics, and math allows you to really mine that and ask the right questions to then use the data in a way that allows you to answer some of these questions. The data sets are just getting bigger and bigger, and so having access to those kinds of things. So I would say if you are interested in astronomy, learning not only the science, and the math is important, but then also a strong background in computers would be very important.
That's good advice. Okay, Harry, you want to comment too, and then I'm going to have Ryan say something.
Yeah, well, I would say, first of all, studying astronomy is great, whether or not you get a job in astronomy. So go do that. And statistics show that people who graduate with an astronomy degree from either undergraduate or graduate school end up employed. They don't always end up as doing, being a professor at a university, but the employment's very good. And in the meantime, you've had a great time learning about astronomy and the universe. So go for it. You'll learn all sorts of skills, and it is hard work to develop the skills. But that's true if you're going to become a musician or a painter or anything. So as long as you enjoy the hard work, you're good.
What was it? Malcolm Gladwell tells us that it takes 10,000 hours to become an expert at something like that.
That's exactly right. I remember that. In fact, and if you add that up, that's about 40 hours a week for 5 years.
Yeah.
That explains my sarcasm.
And how you got there so fast.
Yeah, so quickly.
Okay, Ryan, do you have any advice?
Yeah, Casey and Harry already did a very good job. Study lots of math and computer science and physics, and you'll get yourself there. That's all it takes.
I think Harry brought up a good point too. Is that it's I know for a fact that getting a career in astronomy is not necessarily easy. It's highly, highly competitive. But you brought up the point that you'll end up employed, not necessarily in astronomy or on a tenure track, but with the skills that you're developing with computer science and maths and physics and your analytical thinking allows you to be used in many different fields, not just astronomy.
Good point. And that
astronomy is extremely competitive.
Yeah, and that's the path I took. I did not go to grad school, nor did I to be on the astronomy tenure track, as it's called. But I instead I became a programmer, a software engineer, and became an astronomical programmer. And that says a lot about both my skills as a programmer as well as the kind of programs I wrote. But no, I wrote a lot of astronomy software, and that's where I chose to go. My math skills were not the highest, but they did need to be good, or at least I had to get the math education to do it. But there are many ways of going. If you can build a camera, for example, if you know how to build electronics or build a telescope, those things, all of those skills are in very high demand. So there's lots of ways of going into astronomy without being a, quote, astronomer. But here's the question, guys. I wanted to ask this last week. What's the difference between an astronomer and an astrophysicist?
Wow.
Anybody want to take that one?
Well, Harry actually has a context here too. Is that when we were talking with our astronomers and astrophysicists, we're also talking about dark matter, and we're talking about particle physics as well. And so you have these three-tiered systems where you have an astrophysicist, and so to the astronomer, they're more of a particle physicist, but to the particle physicist, the astrophysicist is more of an astronomer. So there's like that blend there. And especially since we're seeing particle physics being used more in the understanding of cosmology and dark matter, where does it lie? Is it just more physics heavy as far as being astrophysicist, or what are we looking there?
Yeah, I think if you wanted to draw a distinction, it would be along those lines. I tend to use them as synonyms because so much of astronomy right now really is getting at the physics. But there is a sort of a classical of astronomy where you just go out and you try to observe and classify and basically look at the phenomenology of nature. And I think if you wanted to draw a distinction, you might call those people astronomers, and the people who start with the physics textbook or the supercomputer, you might call them astrophysicists. But I don't really draw the distinction.
Yeah, I don't either. I think it's just a matter of what kind of mood you're in and how impressive you want to sound at the dinner party. But here's a question from Dan Buddha. He's asking about the speed of the spin rate of galaxies. Does it change over time? Do they slow down? Do they speed up? Anyone?
That's a really good question. I'm trying to picture in my mind how that actually works. I would say they do speed up slowly over time because they get more mass. And we know one thing. This is just Newtonian gravity. The more mass you have, the faster you're going to spin. And so as you increase your mass, that's also going to increase the spin rate. Now there are all kinds of angular momentum issues you have to take into consideration with doing this. And we know, for example, that the distribution of dark matter really regulates how fast these galaxies are going to spin. But we do see that the larger galaxies spin faster than the smaller galaxies. That tells us how much mass they have. That's, of course, why we also think they're larger. And so that would also explain that as the galaxy gets bigger, its spin rate does go up. That's a really good question.
Yeah. Well, and I think it also should be mentioned, too, is that observing the spin rate of galaxies is one of the primary things that we even notice dark matter in the first place. Is that this is not acting the way it should. It's spinning weird. These outer stars should be flying out into space or going way too fast based on what we're seeing.
Yeah, that's exactly right. That's exactly right, Scott. I mean, that was some of the first evidence. I think it was resolved by Vera Rubin back in the 70s and 80s, collecting this data on how fast galaxies are rotating. And as I recall, people didn't believe her necessarily right away.
No,
yeah.
Right. They didn't. Yeah. So, okay, well, I guess we're approaching the end of the Hangout. Scott, you want to give a quick review, make sure I didn't miss anything? Is there anything you want to mention?
Yeah, I mean, we've had some really good interaction on Twitter. Retweeting. A real big shout out to Texas A&MU Science. Thank you for joining us in our conversation over here too. Cosmic Carol, like that she had a mention about the Hubble Hangout and your fake books. I mean, totally real books in the background. It's just a prop.
They're all real, folks.
They're all real. Let's see here. I think I did want to point out one of the questions here on the Q&A app that we did talk about briefly, but this is from W. Vanderheide, and this is, are there any other ways, theoretically, for spiral galaxies to become an elliptical, except by collision with other galaxies, so very massive one-ring black holes, etc.?
I can take a stab at it, which is more of a speculation, but I think the answer is maybe. This is some recent work that not all spiral galaxies are ultimately going to merge with some other galaxy, but it seems like as they get more massive, they consume all their gas, and so they stop forming stars. What that might mean is, I think Ryan talked a little bit about it, we see these mechanisms now where you can transfer stars from the disk to the central regions of a galaxy. They just sink over time, and that can build up a bulge. And that bulge may, some theory actually speculates that may have the ability to stabilize the gas that's remaining, so we can't form any new stars when it does that. And so as a result, the disk just fades away to nothing, and you're left with this very prominent bulge. They would look more, I think, like the S0 galaxies in the Hubble tuning fork that Ryan talked about at the beginning. So they might have different, subtle differences from true elliptical galaxies that may only be formed through these kind of collisions. That's an open question.
Nice, okay. And there's one here from Ben Etherington. I'm trying to understand the context myself a little bit. I was thinking about this question, but he's asking, do galactic tidal effects transfer, quote, local angular momentum to faster galactic spin? And I don't know if he means the tidal effects of the galaxy itself, or maybe of a galaxy collision. But are there anything that can transfer within the tidal effects, maybe dark matter, something like that, within the galaxy to make it spin faster? Do we know? That's the way I interpreted that question, anyway.
Yeah. I mean, I think you summed it up earlier too. It's just that you're doing conservation of angular momentum, and so if anything's going by and it's transferring that energy, you will see effects, and that's just Newtonian mechanics.
Right. Yeah, so I can imagine that there are probably some ways in which you can affect the spin, like we talked about before.
So that simulation showed when the galaxies were merging, you got those big tails spinning out to large distances. Those we actually call tidal tails. So that is the tidal effect. And what you see is parts of the galaxies go shooting off because they get a lot of angular momentum, and other parts go sinking in because they've actually lost angular momentum.
Right. Okay, so there's one more from Juan Borda. Real quick here. What do you theorize ties both the arms of the tuning fork diagram together besides their shape? So what are there other galactic features and measurements that lead to this shaped diagram? So what gets you to the fork or to the point S0?
So it seems like if you have a spiral galaxy, it seems that from computer simulations we know that it's quite easy to excite a bar. A bar can just happen naturally, and it's a result. It can be a result of tidal effects, for instance. So galaxies can, in the fork part of the diagram, it seems that galaxies can jump back and forth between the normal spirals and the barred spirals.
Oh, really? Oh, that's neat. Okay, cool. Oh, nice. Okay, thank you, Juan. That was a good question. Okay, I think we're going to call it there. We're going to end our hangout there. Scott, what are we doing next week? You want to give us a preview of what we're doing next week?
All the things. I'm still waiting to get confirmation, so I'm still working on that. But
okay. So we're not sure yet.
On some history of the man himself, of Edwin Hubble. So out here in Southern California is the Mount Wilson Observatory, and which is where he made these brilliant discoveries and observations with his team, and with on the shoulders of many other people as well. For when he discovered that the universe itself is expanding, and that was huge in the time. And so, with Mount Wilson being quite out here, I am talking with the Mount Wilson Observatory historical group and seeing if we can get up there. And if you ever have a chance to come out to Southern California, it is a place that you should definitely go visit. It's free to visit, or you can get like a 10-hour tour on the weekend. But you get to see the birthplace of astrophysics as we know it.
Okay. So yeah, stay posted. Well, we'll keep you posted on what the hangout. We're still working out the details. So follow us on at Hubble Telescope, as well as subscribe to our YouTube channel to get notified of these things. So Casey, Harry, Ryan, thank you all for attending. This was a great hangout. Congratulations on the release today. This is excellent science, and I learned a lot about galaxy formation, star formation history today. So thank you all.
Thank you, Tony. Thanks, Scott.
Yeah. All right. Well, that's it for this week, space fans. We will see you next week, and same time. So thank you all for watching, and as always,
keep looking up.
I hope I put that in there. If not, it's hubble25th.org/go/HubbleMania. And then also, the Ode to Hubble video contest finalists have been announced, and that link I did put in the description box. There are 2 categories, those of you who are under 25 and those of you who are over 25, and they've selected the finalists from each category, and they will announce.
I watched a few of them. They're awesome.
Are they?
Really, really good. Yeah.
Yeah. Cool. I need to get over there and watch. I watched a few of them when the voting was going on, but I didn't see the finalists yet, so I'll have to check that out. Anyway, they'll be announcing the winner April 24th, and the winners will get, there'll be 2, 1 in each category, and they will get a piece of the solar array that was actually on Hubble when it was taken down on one of the servicing missions. So that'll be a great prize, I think. So watch out for that. And let's see. Oh, the 3rd episode of the Hubble 25 videos produced by Mary Estacion has been posted on YouTube. That link is also in the description box. She will be releasing 1 video every month for the entire year, all in celebration of Hubble's 25th anniversary. So we hope you'll check that out as well. Okay, today's hangout is about the Milky Way, or at least galaxies like the Milky Way. One of the more challenging things about astronomy and studying the universe is that things take a really long time to happen. Stars take anywhere from 100 million to 1 billion years to live their lives, and galaxies, the same kind of timescales. In fact, we're going to talk about the different kinds of galaxies out there and how long they live, but some of the oldest, like the elliptical galaxies, are almost as old as the universe. So how do you find out? Because by comparison, we're only alive in a blink of an eye in that time. It's 80, 90 years if you're lucky, and or 110 in my case. That's what I just turned 110 today, so I'm going to be.
Congratulations!
I don't look a day over. I'd like Harry, give us a comment a little bit about what Candles is. It's one of the surveys that Hubble has been involved in, but give us a little more specifics. You're muted.
Pushed that by accident. Thank you. So people may be familiar with the deep fields where Hubble has pointed to a tiny, tiny patch of the sky and just taken exposure after exposure for a week or 2 and added them all together. And those are great, and I love those, and I've worked on those, but they're such a tiny piece of the universe that they're not as representative as we would like. And galaxies like the Milky Way are actually pretty rare. And so we need to survey a wider swath of the sky. And we can't invest that much exposure time, so it's shallower exposures, but over much larger areas, 100 times the area more or less of the deep fields. And so ours is sort of it's a statistical survey, taking a bunch of infrared images and then adding them to a database of the optical images that we took of these fields over the years before. With the Hubble ACS camera, and then a lot of information from other telescopes, including the Spitzer Observatory, the Herschel Observatory, the Chandra X-ray Observatory, ground-based telescopes. These are the sort of watering holes in the sky where everybody is going to study galaxy evolution.
I like that. I like that analogy.
Yeah.
That's really cool.
So we've been putting the database together and then starting to mine it, and this was one of the, I think one of the things that we'd hoped to do all along was see if we could put together a story
in various parts of the life cycle of different objects like stars and galaxies. And what our team of astronomers have done today is they have looked at some 24,000 galaxies, and of those, managed to pick out about 2,000 or so that were like the Milky Way and in various stages of their life to try and attempt to build a picture of what our galaxy was like. And they found some really cool things. So let's talk about it right now. With me also is Casey, Dr. Casey Popovich. He's from Texas A&M University, an astronomer / astrophysicist, I assume.
Yes, of course. So, hi, Tony. How are you?
Yeah, one of these days I keep meaning to ask to talk about the difference between the two. Also with me is Harry Ferguson. He's an astronomer at the Institute, and he's a very I love working with him. He's been in our Hangouts. One of the first people that was ever in one of our Hangouts. So welcome, Harry. Also is Ryan Quadri. He's also from Texas A&M, and they're here to discuss what they've done to the universe. So who wants to start? How about you,
What have
Casey?
you done to the universe, guys?
Yeah.
Just so you know, some of my friends here at JPL are Aggies, so I'm sure they will be very excited to know that you guys are on today.
Yeah, I'm sure. So, no,
Casey, why don't you give us a quick overview of what the press release was about today?
yeah, sure. So, this is it was a combination of many different surveys that we have going on, but it focuses really on a big one from Hubble, which is the Candle survey using the Hubble's new infrared imager. Hubble, surveyed all these different fields, getting very deep images. We then combined it with a whole bunch of other data to find galaxies, as far back in time as we can. And we began to find ways to link them together. We get these snapshots in time of what different galaxies looked like. And we started to piece those together to figure out which ones would be most like the progenitors of ones that we see maybe today and nearby, like the Milky Way, for example.
Great. Okay, so you mentioned candles. Hello, Hubblers, and welcome to this week's Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute, and we've done it again. We've got another great hangout planned for you this week. Astronomers, using Hubble and a variety of other telescopes, have looked at some 20,000 galaxies, a little bit more than that, in an attempt to try and understand a little bit more about our own Milky Way galaxy. These are all galaxies that they've looked at individually or in different ways to try to build a story of what our galaxy was like. And we're going to learn about what that story is in just a little bit. I'll introduce him in just a second. But before I get started, let me introduce my co-conspirator, Scott Lewis. He's the internet driver for us, and he monitors all the comments and questions. Welcome, Scott.
How's it going, Tony?
Really good. Carol's not here today for reasons I'm not sure. I think she's on assignment, so hopefully we'll see her next week. But
she's at Hubble. She's up in orbit right now, putting a little thumbnail at the bottom for every picture of her just winking at us. So from now on, every image from Hubble will have Carol winking.
There you go. Oh, there's a thought. Okay, so
I'll do it. Photoshop is my friend.
All right. Well, so before we get to introducing our guests, let me get to a couple of announcements. Hubble Mania is over, and thank you all for voting and everybody who's participated. Turns out the Pillars of Creation was the winner, which I suppose is not a surprise. It's a very iconic image, and for those. Throughout the Hubble Mania campaign, our graphic artists have put together posters that you can print out and download to sort of celebrate Hubble Mania, but it was a big success. Lots of you participated, and we want to thank you for that. The link is down in the description box.
109. Yeah.
I know.
Say that.
So thank you.
Before we get into it, though, let's remind our audience, too, and how they can get in touch with us. So if you're looking to interact with us, we are totally interested in answering your questions and seeing your comments. So the ways that you can do that is if you're watching us right now on either YouTube or Google+, you will see on the bottom left some yellow text saying that we are answering questions live. It'll allow you to use the Q&A app to ask us questions. I've already got it up there, and I'm seeing one comment that's already in here. So that's a great way for us to interact, and actually timestamps it when we're answering your questions. You can leave us comments like you normally do over on YouTube and also on Google+, and then also over on Twitter. We are using the hashtag Hubble Hangout, one word, and we will be I'll be monitoring those, and we'll be live tweeting the Hangout as we're going out from our account at Hubble Telescope. So that is we prefer the Q&A app because it allows us to see live when you guys are doing it, but I love the Twitter conversations that have been happening lately. So please tweet at us, and I might just retweet you if it's awesome.
Yeah, that'd be great. Thanks, Scott. And if you don't follow us on Twitter at Hubble Telescope, please do. Also subscribe to Hubble Site channel on YouTube, and you'll get all of the information on that. Also, Cosmic Carol, I saw your tweet about must not get distracted by deep astronomy bookshelves. It's okay.
It's fake. It's just a poster.
It is not fake. Those are real, and I've read every single one of them. Okay, so today's hangout, folks. in order to understand something that happens over hundreds of millions or billions of years, astronomers have, while we won't be able to just stare at it and see it in our lifetimes, astronomers have some tools that they can use to kind of get a picture of what the lifespans, what happens in